This lesson is about potential divider or voltage divider. Potential divider is useful in circuits to reduce the voltage supply. I'm using this first circuit series to derive a formula for a voltage drop in terms only of the voltage supply and the resistors in series. To drop the voltage on a resistor, I need to add one more resistor in series because the voltage supply is going to share its energy with both resistors. This way, I can drop this voltage across the terminals of this resistor. So let's say if these are the terminals of a voltmeter, and what would be my voltage across this resistor, and I'm going to call this output voltage or Vout. And if this is output voltage, this voltage is going to be the input voltage, Vin. Now the question is, how can I create a shortcut to calculate the output voltage just in terms of Vi, the input voltage, and the resistors, if Vout include the current flowing in the circuit? Now let me start with this equation. So this equation is for circuit in series. So the input voltage is going to be shared between both resistors. So input voltage is equal to the voltage drop over R1 plus the voltage drop over R2. Now the voltage drop on R1 is the current flowing through R1 times the resistance of R1 plus the current flowing through R2 times its resistance. In this step, since current is a common term for both, I'm going to factor it in here, and I can say that my current is Vin, input voltage, over R1 plus R2. And let me call this equation here equation 1. I'm looking for output voltage. So Vout, in this case, is the current flowing on the resistance 2. Vout is my I is Vin over R1 plus R2, all these times R2. Now I have a formula for output voltage in terms of input voltage times the resistor that I want to find the voltage across over R1 plus R2. So I do not have current in this equation, and now I can use this equation to calculate the output voltage on this resistor. Okay, now I have a formula that I can use to calculate the output voltage without any current involved. Now I'm going to use this formula to calculate the output voltage in this circuit. Now I move the value of the resistor to the other side, so I'll have this clean space here that I can plug the numbers. So Vout is Vin is 20 times R2 is this one, 240 over R1 plus R2, in this case 160 plus 240. And this is 12 volts. So after connecting this second resistor with this one here, I reduced the voltage supply from 20 to 12. That's what is called potential divider. In this second circuit, now I'm using a potentiometer. So potentiometer is a device that changes the resistance, and by changing the resistance, I can kind of control how much output voltage I want on this resistor or on this resistor. Depends where I want to reduce the voltage supply. So now instead of having a fixed resistor, I'm using a variable resistor. This is an example of a potentiometer. I have those two screws here that I can connect the wire and make sure they're tight and control the resistance through this knob. Now I'm going to flip this potentiometer to see what is inside. So as you see here, it has 3 terminals, 1, 2, and 3. And this knob changes the resistance between the middle terminal and either one of the outer terminals. In this case, it's connected to this outer terminal here. So this resistance can change from the minimal value up to the maximal value on this potentiometer. This is another type of potentiometer that we use in electronics. We have 3 terminals, and here is indicating 10K. This means 10 kilo ohms, and we have this knob that is changing the value of the resistance. So now, how can we calculate the output voltage on this potentiometer? It's a good strategy to draw 2 lines and indicate what is the output voltage in your circuit. And this is your input voltage. Because potentiometers, they have a minimal and maximal values, we are going to be working only on the extreme range. So in this case, for the minimal value, when the resistance of this potentiometer is 0. So this is my R2. And when this potentiometer is set on its maximal value, which is 20 ohms. This line in the middle indicates like a slider that is moving from 0 to 20 ohms. So I'm using this formula to find the output voltage for this potentiometer. So here is V out is V in, which is 12, times the resistance, which is 0, over R1, which is 10, plus the resistance for the minimum value is 0. So my V out is 0 volts. Now for the maximum value of this potentiometer will give me an output voltage of V in is 12 times now 20 over 10 plus 20. And this is 8 volts. So which means that this potentiometer is reducing the voltage supply, which is 12 volts, up to 8 volts. One of the applications of potentiometers is the audio volume control. Now we have other variable resistors that can be used to control the output voltage of a potential divider, and one is this one right here. This is a thermistor. A thermistor is a resistor that changes its resistance with the temperature. This one here in particular is the NTC thermistor. N stands for negative, T for temperature, and C is for coefficient. So NTC thermistor. This type of resistance decreases as the temperature rises due to an increase in conduction of electrons. This particular thermistor has a maximum resistance of 10 kilo ohms. And when the temperature rises, the resistance decreases. It's very common to use a thermistor to control the temperature in a freezer or even in a refrigerator. So usually thermistors, they are in a refrigerator, for example, is connected to a audio sign like a beep. So when the temperature starts to rise because the door is open, which means the resistance decreases and connects to a audio system, so it starts to make sound in your refrigerator, beep, 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 like close the refrigerator because the internal temperature is rising. Another device commonly used in potential divider is a light-dependent resistor, or LDR. It's also called photocell. It's a resistor that changes its resistance with light. When we have low light, this device has a high resistance. So this is the top of this LDR. So you can see here like a component on the top here that is sensitive to light. So this light-dependent resistor is activated when the amount of light drops to 10 lux. So lux is the amount of light. For example, in a classroom, we have about 300 to 500 lux. So what happened here is when the amount of light drop, so this resistor here, the resistance increases and activates the circuit. Now when the amount of light increases, the resistance decreases, deactivating the system. Can go either or, depends how you set up. So this is a LDR circuit that I have in my classroom. So this is the component. This is the LDR. So this LDR is connected to this LED, this light LED. So when it's dark, look what happened. Dark, I'm gonna turn off the light. So it will send a signal to the LED to turn the light on. So that way that we can control the circuit. Now I'm gonna put the light back on. And now the LED is off. So in summary, those three components, the potentiometer, thermistor, and light-dependent resistor, are the most common components that we can use on potential divider circuits. So let's apply what we have learned about thermistor and potential divider to solve this problem from May-June 2004, paper 2, question 8. A thermistor has resistance 3,900 ohms at 0 degrees Celsius and resistance 1,250 ohms at 30 degrees Celsius. The thermistor is connected into the circuit of figure 8.1 in order to monitor temperature changes. The battery of EMF 1.5 volts has negligible internal resistance and the voltmeter has infinite resistance. One side note about the voltmeter has infinite resistance is because we have here a junction. So the terminal of this voltmeter is connected at this point and this point, create like a pathway for the current to flow. However, since this voltmeter has a very high resistance, the current will not flow through this voltmeter. Will go straight to this resistor. So the only circuit or branch or loop that the current will be flowing will be this one right here. First question, A. The voltmeter is to read 1 volt at 0 degrees Celsius. Show that the resistance of this resistor is 7,800 ohms. So here is kind of the side note that I explain about why the voltmeter must have an infinite resistance is to prevent split current flowing through R. So I'm going to use a potential divider to find the value of this R. So V out is V in times R, this R over the value of the resistance in this thermistor plus R. So by using the potential divider formula, I don't need to calculate the current flowing in the circuit, which will make it easier for me to calculate the resistance that problem is asking. So before proceed, I want to go back to the values of the resistance of this thermistor. So at 0 degrees Celsius, it says that the resistance here is 3,900 ohms. And for 30 degrees Celsius, the resistance is 1,250 ohms. Now, which one should I use? Well, the problem is saying at 0 degrees Celsius. So I should be using this one right here, 3,900 ohms for the value of the term. Now here this problem say the voltmeter is to read 1 volt. So this here is 1 volt and this is my output voltage right here. So then I can say that my output voltage is 1 volt and my input voltage is 1.5 volt. And my R is what I'm looking for, R. And my RT I'm using for 0 degrees Celsius, 3,900 ohms plus my R. So here doing cross multiplication is 1.5 R is equal to 3,900 plus R. Now I'm going to group my R, move it this way, so 1.5 R minus R is equal to 3,900. So now this is 0.5 R is equal to 3,900. So my R is 7,800 ohms. That's the value of my resistor. B. The temperature of the thermistor now is increased to 30 degrees Celsius. Determine the reading of the voltmeter. Again, I'm using the formula for potential divider because it's pretty convenient. So V out is 1.5, which is V in, times the value of the resistor, which I just calculate. This one is a fixed resistor. So that's the value, it's not gonna change. So 7,800. What is changing here is the value of the thermistor because this is the one that changes with the temperature. So now we are talking about 30 degrees Celsius, which is 1,250 plus the value of my resistor. So let's recap. So what this problem now is asking, what is the value of the output voltage of this resistor if the thermistor now is at 30 degrees Celsius? Okay, so 30 degrees Celsius means that this value is 1,250. Because remember the formula is this, right? So my V out, that's what I'm looking for. is Vn, didn't change, the same battery, times the value of the resistor, this one is fixed, 7,800, over the value of the resistance of my thermistor when the temperature is 30 degrees, plus R that I calculate on the prior problem. So this voltmeter should be reading now 1.3 volts. So there is a reduction of the voltage supply, and that's what we are doing with potential divider type of problem. We are reducing the voltage, getting a fraction of this voltage on certain sections of your circuit. So this is 1.3 volts. Next question. The voltmeter on this picture here, this voltmeter is now replaced with one having a resistance of 7,800 ohms. Now calculate the reading on this voltmeter for the thermistor at the temperature at 0 degrees Celsius. What this problem is saying that I have to replace this voltmeter with another resistor with the same value of this resistor here, which is 7,800 ohms. And is asking to calculate the output voltage for this scenario when the thermistor is at the temperature of 0 degrees Celsius. So 0 degrees Celsius is 3,900 ohms. So right here, we have in front of you the whole circuit, the whole story. So 1.5 volts, this is your thermistor, 3,900 ohms, because this is at 0 degrees Celsius. And now the voltmeter is being replaced by another resistor with the same value. And what will be now the output voltage? So a couple of things we need to do before calculate all this. Number one, because those two resistors, they are the same and they are in parallel, I can calculate the equivalent resistor for those two values, which is, because they are equal, 7,800 divided by 2, okay? Not 3,900 ohms. Then my output voltage will be the input voltage, which is 1.5 times, because this is where I want to calculate my output voltage. So it's right here, which is 3,900 over the value of the thermistor for 0 degrees, which is 3,900 plus 3,900, and plug in the calculator. The output voltage is 0.75 volts. Can drop about half of the voltage supply, which is 1.5 volts. A multiple choice that combines the LDR and a variable resistor in series. So let's read. A potential divider consists of a light-dependent resistor in series with a variable resistor of resistance R. The resistance of the LDR decreases when the light level increases. The variable resistor can be set at either high resistance or low resistance. Which situation gives the largest output voltage? Right here. So this problem states that the resistance of the LDR decreases when the light level increases. As far for this variable resistor, we have two sets, a minimum and a maximum. So in order for this resistor draw all the energy for itself, must be at a maximum setting. So this is a hungry resistor. It's going to eat up all this energy as much as it can. So that's the idea. So greater their resistance, more voltage drop we have here. So the output voltage will be high, which means that one factor we got figured out. So R must be at high setting in order to get the highest output voltage. But what about LDR? How we are going to set this? So you don't want this guy competing with this. So this guy needs to be at low value. So it's going to have a low value when the light is high. So light must be high. Now let's find the perfect matching. So here for the LDR must be high, and for the variable resistor must be high. So here A, high, high, and this is the winner. Now we have another potential divider type of problem with a variable resistor and a fixed resistor. So let's read. The diagram shows a potential divider circuit designed to provide a variable output PD right here. Is variable because it's going to change value, right? It's variable resistor. Which row gives the available range of output PD? So let's calculate for the minimum range for this variable resistor and the maximum range for the same one. For the minimum range will be 0 ohms. That's the minimum. And the maximum R will be 5 kilo ohms. To solve this problem, I'm using the output voltage for potential divider. Be careful with this one because now the resistor that I want to calculate the output is on R1, not on R2. So when you multiply, the input voltage must be times on the resistor that you need to calculate the output voltage. In this case, it's R1. And then you have to add both. So in this case here, will be my input is 9 times 0 over 0 plus 5K. Which means when this resistor, the variable resistor, is at the minimum setting, the output voltage is 0. What about when it's the maximum setting? So now the out is 9 times 5K over 5K plus 5K. You add both resistors. So now the out is 9 times 5K over 10K. To make my math a little bit easier, I'm gonna cancel those K's. And V out is 4.5 volts. Okay, so now I need to find the range on the options. And for the maximum output is 4.5 and minimum is 0. So this is the correct answer, B.